All right. This lecture is about to get a bit macabre. We are dealing with bloodstain patterns, trying to reconstruct the crime that happened, the violent crime that happened, using the bloodstains that are left behind. Now, it's kind of obvious that when you have a violent crime, you're going to see some blood. So we want to, and generally the criminals who do these violent crimes do not clean up the blood. And even if they do, there are ways of finding the blood, but of where the blood was. But in any event, when we see the blood, we should be able to, or we can, reconstruct the crime and find out what happened. And this is very important. But you are warned that you're going to be seeing blood and a lot of horrifying things in this lecture. So be warned. What we really want to do is reconstruct the crime using the clues that we have. And with this, we can find out more information. Now, the best way to do this, to reconstruct the crime, would be, of course, to have a witness or a video camera. But if you don't have that, and if you only have a witness who might be biased, really the only way to do it is using the evidence. And we can use what's called blood spatter, where the location of blood left behind, to reconstruct the violent crime that occurred to create the blood. So what we can do now is watch the world's greatest detective in how he used this reconstruction to find something interesting, and even the murderer, even the identification and location of the murderer, using crime scene reconstruction that started with blood spatter analysis. So let's see it. He's
Spatter
reconstructing the crime.
analysis indicates the shot came from below. Grant must have dropped the camera when he was hit. Reviewing the reconstruction will help me find it, assuming the shooter didn't get there first. Alfred,
Sir?
I'm sending you some data taken from a camera. See if you can ID the subject in the shots.
Certainly, sir. Just give me a moment. Here we are. One Chucky Burks. I'm sending you his last known location.
Interesting. He was able, because he reconstructed the crime, he found a camera. And with a picture of the camera, he found the murderer. Well, anyway, back to the real world. The fact is that violent crime produces blood. You're going to get through the skin because of the violence, and a lot of blood can be produced, which will be seen unless everything was cleaned up. But again, you can certainly find blood, and that will give you evidence, and that will tell you a lot of things about what actually happened. One, the location of the victim. I mean, that's where, well, the victim bled. So you know the blood is, you know something about the location of the victim. Some of his actions, was he panicking or not? Some of you can know how many blows of, let's say, a pipe was delivered. You might want to know where the attacker was. And other parts of the story, maybe the way the blood was, you could see the body was moved, or maybe where the criminal, where the attacker went afterwards. We can see there are many things that can be gained by knowing how to interpret the bloodstains left behind. One thing that we should know is what they call what does blood look like when it hits, and how to analyze it when you see it. There's something called satellite spatter. That's if a drop of blood falls on the surface, the edges kind of like stretch out. That's a satellite spatter. You can see, like here, for example, in this case, the blood hit over here. That little thing over here, little piece of blood that kind of like bounced off or like stretched out and detached. That would be your satellite spatter. And in this case, what it can do is it tells you the direction of the blood. The blood was flowing in this direction, and that's what this satellite spatter is. That's what it shows. Another thing that is actually very important is the length of this blood drop. If it's not circular, if it's not circular, then I can tell you the angle at which it hit this surface. If it's a circle, it hit from directly above. If it's not, you can tell the angle, and you can certainly tell the direction based, using this satellite, the satellite spatter over here. So we'll show a little bit about how this works. What is done is they use the inverse sine. You're probably familiar with this from high school. It's you know about sine, cosine, and tangent. The sine of an angle, the sine is the opposite divided by the hypotenuse. The sine of an angle is a certain number that comes from a certain angle. Now, this is the inverse sine, or the arc sine. You can find it on any scientific calculator. You'll find how to, it's a button there. The sine of an angle gives you a certain number. Now, you can also say that if I have this number, I can find the angle that produces this sine. It's the inverse of the sine. The sine of a certain number will give you the sine of an angle will give you a number. The arc sine, or the inverse sine of that number, will give you the angle. And that is how it's done. We take the arc sine of a number. We'll show you how you get the number. The inverse sine of that number, and we will reconstruct the angle that the blood hit. This is how it's done. Here we have a circular stain. We're saying it's 2.5 millimeters by 2.5 millimeters. It's a circle, so of course the length and the width and the height are going to be the same. So if it's a circle, we take, in this case, 2.5 millimeters by 2.5 millimeters. That's, again, I've just made up these numbers. Blood drops can be larger or smaller than this, depending on what causes the blood stain or the blood drop. So here we have, we take the width, that's in this case top to bottom, because the length is always the longer one. See here, this is the length, top to bottom is the width. You can call it the height, but I'm calling it the width. Okay, so the sine of the width, that's 2.5 millimeters, divided by the length, which is also 2.5 millimeters. After all, it's a circle. Here's your width, here's your length, they're the same 2.5 millimeters. So the inverse sine, or the arc sine of 2.5 divided by 2.5, that's our number, will give you an angle. Remember, the inverse sine of a number will give you the angle. The inverse sine of the 2.5 over 2.5, the width divided by the length, is the inverse sine of that number, will give you the angle. This is 90 degrees. And this actually makes a lot of sense. If the blood came from directly overhead, it'll land in a perfect circle. We are assuming a spherical blood drop, which is, again, it's generally assumed. It's a good estimation that the blood is roughly spherical. So when it lands flat, it'll form a circular stain. Now, if it does not land flat, like, directly on there, it's like at an angle, pushed at an angle. Here we're talking about some vector that's pushing it to the side. Instead of falling directly here, it's pushed to the side. Then instead of being a circle, it'll be stretched to the side. So that stretching makes the length a bit more. In this case, but we use the same arc sine, the same inverse sine, same width divided by the length. Here, in this case, the length is 3.0. That's what I made it. So same width. So the inverse sine of the width divided by the length, that gives you a number. Inverse sine of this number gives you an angle. That is 56 degrees. That means we can tell that this thing was not at 90 degrees, not directly overhead, but at 56